Hello everyone, this is Mr. Daban, teaching Chapter 7, Section 3. The section is about current and resistance, which those two concepts are very useful in electricity. I explained these two concepts to three classes, I guess, but two of the other classes, not all the students came back, so I didn't have a chance to explain the concepts to everyone. So hopefully this this video, will be a revision for those who came, and a brief introduction for those who did not come. So hopefully both of the parts will benefit from this. Definitely recommend it for everyone. First I'll introduce what a current is, and then I'll introduce what a resistance is. I'll not give a very in-depth, detailed explanation. I'll just try to give, as they say, the tip of the iceberg. Just the very general basic concepts, nothing in depth. All right, let's start with the idea of a current. What is a current? You got to keep it in mind that so far that we've been studying electricity in our book, mostly, not always, but mostly, what we took was what we called static electricity. Static electricity is basically when you have a charge, but it's static. It's not a moving charge, at least not a controlled moving charge. So we took that was what we had as static electricity. For example, a very good example for static electricity was when we used the balloon and rubbed it against the hair, and the balloon became charged. But all that charge was stuck on the balloon. The charges were stuck on the balloon. They couldn't move. They didn't have a path to move through. That's what we call this static electricity. Static electricity, although it's useful, but unless you have moving charges, only then the great applications arise. So the electricity that we use in our daily life are not static electricity, the things that we use for our electronic devices. It's what we call a moving charge. So what we are taking in our daily life, all the devices, the electronic devices that we have a control of the movement of the current of the electric charges inside. You have an electronic device, there are charges moving through them, and we control the movement of these charges. The movement of these charges inside, let's say, a wire or a conductor or an electronic device is known as a current. So from here on, we're not taking static electricity, we're talking about moving charges, what we call a current. So a current is basically charges moving through a wire, moving through a conductor, whatever you want to call it. And this is really important because it gives us a lot of applications. All the electronic devices that you see around you, such as a light bulb, let's say, or a radio, or a television set, or an air conditioner, a refrigerator, an automobile engine, all of these instruments that you just heard, currents are passing through them. Without currents, without a controlled movement of electric charge, these instruments wouldn't be possible. All right? So this is very important. The remaining of the page is trying to talk about that current is even there, even present in a human body, even us. Our biology uses current as well. For example, the way that electronic signals are transmitted between my body to my brain is happening due to the current. It's a transmission of charges that goes, a signal that goes from, let's say, my body all the way to my brain, and my brain responds to that signal. This is all due to currents, charges in motion. So we learned that a current is when a charge is in motion, its charge is moving. Okay, let's define current a little bit better. This is the definition on the left side that you see. Electric current is the rate at which electric charges pass through a given area in a given time. All right, so this will be the idea of a current. You can see the equation on the right side in the middle of the page. Here, you can see that current is basically delta Q. Current, the symbol for it is I, as you can see. I equals to delta Q over delta T. What does delta Q stand for? Delta Q simply stands for the amount of charge that is passing by through a given area. And delta T is the time interval. how long does it take for these charges to pass? Does it take 1 second, 2 seconds, a minute? How much time does it take for the charges to pass? So delta Q is the charges passing through a given area, and delta T is the time interval. Divide those two, the ratio will make electric current. And what was the symbol for electric current? I. I is the symbol for electric current. Once you measure the electric current, let's say you get a number, let's say 20. How do you measure it? In what unit do you measure it? In units of ampere. So the unit is simply A, capital A in English. This is your unit for electric current. If you have a wire, if a lot of charges pass by, that means the current is high. So that means charge and current are directly proportional. More charges go, that means more current you have. What about for time? Well, the proportionality for time and current are inversely proportional. If it takes a lot of time for the charges to move, that means you don't have a lot of current because it's taking a lot of time for these charges to pass by. So that means you have low current. So time and current are inversely proportional. Charge and current are directly proportional. So you know the equation, you know the proportionality, you know the SI unit, which is ampere, and ampere stands for, as you can already guess, for charge it's coulomb, and for time it's second, so it's coulomb per second. That's what ampere means. Simple as that. All right. So I think this is a very, very brief introduction for what a current is. It's the number of charges that pass through a wire in a given time. And that's it. Simple as that. So let's do an example, a sample problem. Let's solve a question. Try to find a quantity using the current equation. Here the question says the current in a light bulb is this much. So you have the current given, and the symbol for current is, we said, capital I in English. How long does it take for the total charge of 1.67 coulomb, that is obviously Q, this is charge, and how long does it take? That means time is unknown, so T is unknown. Okay, I is given, current is given, Q is given, charge is given, time is unknown. Very, very easily solved. Let's write down the equation for current. The equation was simple. It was I equals to delta Q over delta T. And this equation has to be rearranged because what is unknown is the time. So I got to rearrange the equation. And usually when the denominator is unknown, just switch places. So the equation will become delta T equals to delta Q divided by current. That's it. Put the numbers back in. Delta Q is 1.67. I is 0.835. You divide those two numbers, you will get your value. And the unit for this question, because we solved time, that means the unit is in seconds. So whatever you find, put it in your calculator, you will measure this in seconds. I think this sample problem will be a good idea, will give you a good idea. Probably solve only the first question, or maybe the second question as well. Solve a couple of questions, don't go in depth, don't solve all the questions, you don't need to, because I'll not go into detail for this section. Just have an idea what's going on, and you will do fine. For example, this question says if the current in a wire of a CD player is this much, you can see that this is 5 milliampere. If you see the word milli, as you know, you have to multiply your quantity by 10 to the power of -3. Or you can divide it by 1000. Same thing, no difference. How long does it take? Time is unknown again, just like the sample problem, nothing new. Charge is also given, Q is also given. Do the same thing, guys. That's it. For the next question, it's micro. Be careful, micro is 10 to the power of -6. So keep these things in mind. I'm sure you will do totally fine for current. So I don't think you have problems with current now. You know the definition, you know the equation, you know the unit, and you know how to solve the sample problems and the practices. Simple as that. Let's move on to the new concept, the other concept, the second one, which is resistance. Now, we said current is basically charges that are moving. If I draw this, you have a wire here, and there are charges. These are, let's say, electrons inside the wire. These are charges, and these charges are going. That was a current, right? That was what we called I. This is what I explained just now. But these charges, when they pass by through this wire, it's not a paved, easy path. There is resistance through the way. It's like you going through mud. It's not an easy path. You're being resisted by the path. This resisting force that you face on the way is what we call resistance. Simple as that. What is resisting you? What is resisting these charges? The materials of the wire, the path itself, the atoms that make the wire, or the ions that make the wire, let's say. So it's the wire that has resistance, because this wire is made of atoms. When these charges pass by, they bump onto these atoms and they slow down, let's say, or they lose energy, let's say. They're being resisted. So resistance is basically the opposition to the motion of the charges through a wire, through a conductor. This is what we call resistance. Very, very easy. Nothing difficult here. So we know what resistance is. The symbol for resistance is R. That's how you write it in an equation. And this is the equation for resistance. Resistance is basically potential difference, because delta V is potential difference, as you know, divided by the current, which is I. So delta V divided by I. This is your equation, resistance. All right. So we know now that this equation is the equation for resistance. This equation is what we call Ohm's law. Usually it's being called Ohm's law, O-H-M, Ohm's law. All right. Usually you see this equation in other forms as well. For example, I've seen it a lot written as I equals to, the equation, usually you see it this way, delta V equals to I multiplied by R, which means current multiplied by R. This is how I usually see it. But I think a better way to visualize this equation will be if you write it in terms of current. Current equals to delta V divided by the resistance. This is also another way to write down this equation. We use this equation to find the resistance, but you can also use it to find current, or you can use it to find potential difference. I'll show some simulations in a minute and solve a couple of questions, but before that, I would like to talk about the proportionality of the equation, right? I mean, what happens if I increase potential difference, delta V? If I increase delta V, what do you think will happen to the current? I increase delta V, you guys already know, I'm sure, that current will increase with it. If I have a lot of potential difference, more current will pass by, okay? And if I have a lot of resistance, less current will pass by, because there is a lot of resistance. That's why there's a lot of resistance, a lot of opposition to the motion of the charge. So the resistance will not allow the charges to move easily. Okay, what about the unit for resistance? Well, the unit is what we call ohm. All right, this is the omega, that's the symbol. That's the Greek letter. This stands for ohm. And this is basically 1 volt per ampere, because the unit for potential difference is volt and the unit for current is ampere. So it's volt per ampere, which is what we call ohm, O-H-M. And the symbol is a Greek letter, which is what we call omega. All right, let's solve a couple of questions. Yeah, before I solve the questions, I think this picture that you see here explains the whole thing very well. This green guy that you see through this wire it's written ampere. That means this is current, this is I, trying to pass by, trying to go through the wire. What makes it go through the wire? The volt is trying to push it through the wire, delta V. But ohm, which is resistance, tries to capture it, tries to oppose its motion, doesn't let it go. So if I show the equation one more time, current equals to delta V divided by R. Delta V, volt, if I increase it, current increases, because volt wants to push the current. What about the resistance? If you have more resistance, resistance wants to make it stop. It captures it. It opposes its motion, doesn't let it to go. So I think this illustration here that you see explains the whole thing very well. Volt is pushing current, resistance is opposing it, doesn't let it to go. That's it, simple as that. So if you have a wire, how can you make a wire that have the least amount of resistance? Okay, Or maybe you want to have a lot of resistance. It depends on it depends on what you want. Sometimes you want to control current. You don't want a lot of current to go. You want to control it. Maybe this is what you need. So how can you make the least amount of resistance, or how can you make the greatest amount of resistance? There are 4 ways to do this. Okay, the first thing is to talk about the length. If the wire is short, if the length is short, this one is the short side as you can see, then the resistance will be less. But if the wire is long, then the resistance is a lot. Imagine you going through mud, as I said. If the path is short, if it's only, let's say, a couple of meters of mud, not much resistance. Okay, maybe you become late because you're going through this mud and it's difficult, but it's only a couple of seconds and then that's it. So not a lot of resistance. But if it's 1 kilometer of a mudded path, right, then that's a lot of resistance. The more the road, the longer the wire, more resistance. Because longer the wire, more atoms are in there, and you bump into a lot of atoms. So that's why there's more resistance. What about the area? Well, it's also obvious. If the area is big, if it's wide, the cross-sectional area, then you have a lot of space to walk through. You're not being confined into a tiny space, so less resistance. But what about if the wire is very narrow and it's very tight and you cannot move through it easily? So that means a lot of resistance here. Okay, the type of the material also affects it. Some materials by nature, in nature themselves, that's their property, that's their behavior, their characteristic. Some materials in nature, by nature, are less in resistance, such as a copper, which is what you see in a wire. Iron, on the other hand, has more resistance. Okay, so this is the property of the material. Some materials have less resistivity, some materials have high resistivity. Okay, the next thing is temperature. If the temperature is low, okay, which is the first case, then resistance will also be low, because the atoms inside this wire, which are opposing the motion, which are opposing the charge, they're not moving very fast. Therefore, when the charge is trying to pass by, they don't bump into these charges a lot, because they're not moving a lot. Imagine you passing through your school's corridor, okay, and there are a lot of students there, but it's very cold, so the students are not energetic. They're all sitting down in a corner, so you can pass by easily because they're not moving, they're not bumping into you. But imagine if it's really hot and the students are very energetic and they're moving all around and you're trying to pass by. What happens to you? All the students will bump into you. They will resist your motion, right? So more temperature, more resistance. Less temperature, less resistance. And that's why, if you remember, we said superconductors only exist in extremely low temperatures, because the lower the temperature, less resistance, more conductivity. That's why you get superconductors in that case. So definitely understand this table. Very important. All right, let's solve a question. Resistance of a steam iron is 19 ohm. This is R, that's resistance. What is the current? I is unknown. If it is connected to a potential difference of 120 volt, that's delta V. Let's find I. I is simply delta V directly proportional divided by resistance inversely proportional. Right, let's put the numbers back in. Delta V is 120 volt divided by the resistance, which is 19 ohm. And you divide those two numbers, you will get your value. And the unit will be in ampere, because ampere means volt per ohm. That's it. Do your math. Nothing difficult, nothing challenging here. Let's move on to the practice. In the practice here, I have a battery, which is 1.5 volt. This is delta V, that's potential difference. This is resistance, that's R. And this is the current, that's I. Again, same equation, same thing. Do the same thing. Next question, same thing. The other question, same thing. No challenges here, guys. Solve probably 1 or 2 questions. You will do totally fine. So before I end the lesson, I think this is it. You get the whole idea. But before I end the lesson, I would like to show this simulation, and then we will call it a lesson. So here in this simulation, I have a wire. All right, and this is my wire, and I will try to make the wire a little bit long. And you can see inside this wire there are charges. You see these negative blue things inside. These are electrons. These are charges in the wire. They try to pass by. You can see that these charges are stationary at the moment. These are static charges, not moving. How can I make them move? If I add a battery to it. So I'll add this battery here to this wire in a minute. Let me make a circuit, close this wire so that you can see these charges are going. If I close the circuit, if I add the wire to the positive and to the negative terminal of the battery, then these charges will start to move, as you can see. You see that? If you add a battery, that means you're applying potential difference on the wire. Apply potential difference on the wire. Delta V will make the charges go. Take it away, the charges will not go. If you don't have delta V, if delta V is 0, if potential difference is 0, no current you have. That means no charges are going. You don't have a current. But if there is a delta V, then the currents are going. Okay, that's very, very easy to understand. How about if I add a light bulb? A very good idea. Add a light bulb, and this should turn on. Why is it not turning on? I think I'm not connecting it very good. Let me connect this in a better way. So this is your light bulb. Let me make a better circuit. Okay, so yeah, this is connected here. Let me connect this wire to the other end of the bulb, and this light bulb should turn on. Yeah, now it should turn on, as you can see. Now you have the current going through the wire, and they're going through the light bulb, and the light bulb turns on. This is how you get light bulbs. This is how you get light, and this is how it works. All the devices that you have, all the electronic devices that you have, this is how it goes. You can already notice that the charge is now moving a bit slower. Now, because this light bulb is acting as a resistance in this case, do you see the filament inside the light bulb made of some type of wire? This wire have a lot of resistance. So the current, the charges, when they try to pass through this filament, they bump against the atoms, and then they lose energy. They get hot, and they radiate, and that's what you see this light being produced. Okay, what about if I increase the charge? I think there was something that I could do about the charge. Yeah, I could increase I can increase the potential difference. This battery that you see, how about I increase the potential difference? What do you think you will see? You will see more charges passing by. Because we said if you increase delta V, current will increase. Delta V and I are directly proportional. So this is 9 volt, but if I change it to 30 volt, 50 volt, as you can see, more current. Increase delta V, current will increase. Increase potential difference, current will increase. Obviously, you see more light produced. You see the charges are passing by faster in shorter amount of time. The time becomes less, the current increases, as you can see. Very, very nicely shown. Okay, so that's the idea. I think to understand this, that would be enough. This kind of like gives away the whole idea. I think this is all very understandable, very, very straightforward. I hope you guys understood. If you have any questions, you should let me know. If anything was not clear throughout the whole tutorial, do let me know. I hope you guys understood. I hope you do good in the exam. I believe in you. I think you guys will do great. Good luck. That's it from my side. Best of luck, guys. See you in the exam.